started. Okay, so I was gonna talk about the problems in chapter 10, the first 5. And specifically the first 3 are about this link that they're not about this link. They're about an example that I kind of did last time, but I didn't actually really do the whole thing out. But they're from this link that's on the Slack chat that someone, Ashley sent, which I literally was trying to find a resource to show people it, and I found it, and I was about to post it, and I was like, maybe I should check if it's the same as, and it's exactly the same as what she. So anyway, but I can go over that now. I mean, that effectively has all the pieces in it, but obviously you're in a class where someone.
I couldn't relate it to the problem.
That's fine. That's fine. Yeah. You're right.
And it was like, just follow along. I'm like, I'm gone. Nope.
Yeah. so I'll go through and skip
real quick.
because I think they at the end set all the lengths to be the same, which we're not going to do. So hold on. There we go. Okay. So I'll go through it, specifically the parts that we need. And the problem let me write this out. X, Y, Z plus, okay, so this is going to be sort of a different shape than the normal one we write. Normally I write the V on the other side, but obviously this is the same thing. Okay, and now and this is all the V, so here's the Schrodinger. This is always true, of course, as we all know, the Schrodinger equation, but the problem they're asking about is is it the 3 lengths are all different?
It's 1, 1.
Well, it's okay. I'll just do it where the lengths are just L, because as usual, if we just put numbers in, it's not going to make any sense. So, so I'll do it in a box. There's literally a particle in a box. You can actually Google particle in a box, and on Wikipedia, there's a page called Particle in a Box, where they literally do this problem. So that's sort of like what it's called. I'll call this L1. Hi. Oh, hi.
You gotta be quiet. You.
Ashley.
LZ. Okay, so it's so this is the box. This is the potential, actually, of course, what I'm drawing here. This is not the wave function is not anything like that. Outside the box, the potential is infinity. I don't know how to, it looks just like it's hairy now. Anyway, whatever. The point is that the box, it's like there's infinite potential everywhere, meaning you cannot penetrate, the wave function cannot penetrate into it anywhere, except for in the box where there's 0. So if we wanted to write this in terms of, actually, hold on, I'm going to make sure my computer doesn't go to sleep. Okay. Do you know if you have a Mac? Actually, if you have a Mac and you don't want your computer to go to sleep, you can go on terminal, the command thing, and type in caffeinate, and it'll just keep it awake.
What?
Little tip. That's what I do when I upload the videos, because it takes like 2 hours, and if it goes to sleep, it'll stop. So
It's such a weird classic Mac thing.
you could do caffeinate and then -T and then the number of seconds you want it to, if you want it to shut down eventually. But anyway, sorry. So, side note. I don't know if it works for Windows. It probably doesn't. But.
Yeah, Windows go.
They don't do anything fun like that.
Sorry. So I'll write, if you wanted to write it out mathematically, like in a form where you didn't want to draw a thing, of course, if they could call it 3D infinite square, so I'm just giving you, these are like 3 separate names for this same problem. The problem is a 3D infinite square well, or infinite quantum well, whatever. They could draw it where they said the wave function is only allowed to be in this cube where, that's not a cube, sorry, it's a, box with 3 different lengths in general. In the problem they give you the actual numbers. As usual, that's not going to be interesting we're going to have to leave the variables here. And this will be infinity from, sorry, how do I want to write this? Well, I'll say 0 from 0 from what is it? X equals 0 to Lx, y, Ly, 0 to Lz. Okay, and then infinity, I mean elsewhere. You could just, of course, you could write x is greater than Lx and less than 0, and then you could write the whole thing out. But anyway, these are just all ways to write a box. Specifically choosing the parameterization where the origin, x0, 0, 0 is one of the corners, and the opposite corner, which is this one, is Lx, Ly, Lz. I don't know if that's exactly the one they use in this page. Yeah. Oh, they do. Okay, they write it in a really weird... Wait a minute. No, they don't. Whatever, it doesn't matter. Okay. So now, okay, so this is all how you'd write it. Now I'm going to erase these ones because we just need to look at the box. We don't need to, see how you write this. It's also written on the webpage thing anyway. So now we can replace, now this is it's a 3D problem, so this Laplacian here is equal to d squared dx squared. We're using partial derivatives now. Now normally if it was just d dx of psi, that would be the normal 1D Schrodinger equation that we've been using. But because it has 3 variables, it's a 3D equation, we have to use the partial derivative. Doesn't really matter too much. I don't think you'll get points off or anything, but that's why we're using a different symbol. So it's this, psi, is this term right here, right? And then v is, well, we're going to just do the wave function inside, because we know it's 0 elsewhere. So v is actually going to be 0 for the inside portion, and we get this. Now this is what's called a separable differential equation. I'm worried about this markers. That's a little better. Not going on here. So this is called a separable equation. Now what that means is, well, how you tell if it's separable, they'll generally always be separable. One of the reasons you can tell is because everything is independent of the other coordinates. So the v doesn't have any coordinate dependence here, and it looks like you could write it. Remember I was saying last time, I kind of said it. I didn't really do anything with it, but I said that you could write it as 3 separate equations. Turns out that's actually completely true. It's called separable, and we can literally write this as d squared dx. Well, so the first step we would do is, if we want to do this formally, we would write psi as x of x times y of y times z of z. This is technically how we do it. And what this means, this big letter x, y, and z are functions. So psi is a function of x, y, z. It's a 3-dimensional function, x, y, z. But we can write it as just the product of 3 separate 1-dimensional functions. Okay, does that make sense? It seems really weird that you could do this. You can't actually do this in general. But in this case, we know we can because there's no mixing of the coordinates anywhere. So don't worry if that's not, if you were like, I wouldn't think of doing that. That's true. No one thought of doing this until like 1700. So many people didn't think of this. Anyway, it doesn't matter. The point of all this I'm just showing you is just to get to the solution, the forms of the solutions. So don't worry too much if you're not exactly, hopefully you're following it, but you don't have to be able to reproduce things that are harder than this. So this is the form, okay, of a separable equation. Now if we actually plug in this form, now remember the point of these differential equation solutions is that we get a form, like e to the minus ax or whatever, and we just plug it back into the equation and we just find whatever we find. Like we solve for one of the variables. So if we plug this back in, so let me write psi, so psi goes here, x times y times z, I'm going to leave off the dependence here, equals e psi, and then of course we get another equation, 2m y squared times x, y, z put those in parentheses, equals E psi, right? And psi, of course, is still x, y, z, but I didn't. Anyway, whatever. The point is that, and then we get a third one. The point is that, all right, I'm going to erase this for now, but remember there's three. I'm just dealing with one of them right now. They're all going to be the same anyway. That this and here, because y and z don't depend on x at all, when I take the derivative of this with respect to x, I'm going to get, it'll basically be this, right, times y z equals e x y z, okay? So all I did was I took one of the three equations that we have here, if you break it all apart, and wrote it in terms of this separated wave function where I wrote the dependence separately. And now because I separate, the reason I was separating in the first place is so I could write it like this. Because when I take the x derivative, one of the terms, the y and z don't do anything. The derivative with respect to them is 0. So by the chain rule, this would be 3 terms, right? By the chain rule, no, product rule. Right, by the product rule, I would get 3 terms, but the other ones don't do anything. And the good thing about this is now we can cancel the y and z. And now what do we have? Just this is exactly what we did, like literally the only thing we've done this entire, in every office hours this whole semester is this thing, right? We've just done, well, not, basically this with boundary conditions. This is the 1D Schrodinger equation. So we know the solutions, and remember it's x still, it's not the whole thing yet, it's just still x. The solutions look like radical 2 over over Lx. So I'm going to write, so remember how we got, well, I'll write it first and I'll explain. Sine n pi x over Lx. I believe that's, yeah. Something like this. Yes. Understand why these markers work. Okay. So how we got this sign here is because of the thing. Oh wait. Sorry. What happened to? Oh, okay. Okay. We're fine. For some reason that made me a little nervous. Okay. Anyway, sorry. So how we got this, remember we did this last time, how we got this was, this is essentially a equation that says that the negative derivative of some function is equal to itself, and that function looks like sine, right? And then when we normalize it, remember we have to normalize, like normalizing means we take the wave function squared and integrate it over all of space, but of course over all of space in the x direction just means between 0 and Lx, this must be equal to 1, and then we can solve for the constant out front. Really it's like a psi is the wave function, and so squaring it gives you a squared psi squared, and then we can solve for a is square root of 2 over L of x or something. So that was just how we solved that thing. Okay, so that's x of x. So that's the x component of this. But of course, you can imagine, I didn't do anything. It doesn't matter that it's x here. If I replaced this with y, so I'm doing the y component, then I will get a different function with y of y, and if I replace it with z, I would get z of z. And so the entire wave function is actually going to be something, and I'll figure it out in a second, times sine of n. Now I should really write this as nx, because there's going to be other n's. Each time I do it, if I do it with y, I get a different n, of course. nx pi x over Lx times sine of ny pi y over ly times sine of nz pi z over lz. And then this is going to be square root of 8 over lx, ly, lz, I guess. Just make sure that. Yeah, square root of 8 over v. So they write in the notes, they write v as the volume, which is just, of course, lx, ly, lz. And the 8 is from the 2's on top. Okay, and now, so let me box this in red. So remember I was saying last time when I was talking about the
Is the
Yeah.
first term squared or is it?
to the
square
1/2.
root? Oh, okay.
Sorry, it's I just realized that I should have put a square root, but
I just didn't know.
no. Thank you. It's these markers are not very good. So remember last time I was talking about how with the hydrogen atom we have the principal, we have the like 3 quantum numbers. We have n, l, and m, right? And they mean whatever. I don't know, what principal and magnetic and something. Hey, whatever it doesn't matter. The point is that in some of these systems we have different quantum numbers that tell you about the system. In this case, we see them. They're these numbers here. They're integers. So this is actually like you should really write psi of n, x, ny, and z. And of course, it's a function of coordinates. Why do I keep writing x, y, z? So I'm just trying to emphasize that the psi is a function of x, y, z. It's always a function of x, y, z, but there's actually, of course, there's many wave functions. And to tell me the wave function, you have to tell me nx, ny, and nz. Like all 3. So that's it. I should say that's it for the wave functions. Now to find the total energies, remember the other thing we have to, basically all these quantum mechanics problems are start with the potential and you got to find the wave functions and the energy. But now that we have the wave functions, of course, with the Schrodinger equation, we should have the energies pretty quickly. We just plug them in, and that's what we can do. So let's erase a bunch of this. And then I'll erase this. So here's the wave function. Here's the Schrodinger equation. That should be all we need. I'll leave this up for now, even though even though this is the point of that. And now, so let's plug it in. Well, this is going to be x squared of, let's not worry about this for now. Well, I'll check at the end that I have the right, it is going to matter. Well, whatever. So what do we get when we plug this function? It's just the product of 3 sine functions. Well, the first one, I'll just say psi because I don't want to write them all. As we just saw with this whole thing, the x one is only going to act on this one. The y one is only going to act on this one, and the z one is only going to act on this one. And because it's the product rule, we're not going to have to worry about those things. So if we write dx, so this squared, the second derivative, so 8 over v. I'm going to start writing v now for the volume of the box here. So just to change so I don't have to keep writing it. And now the second derivative of this is going to be n squared pi squared over lx squared, okay? And that's this term. And now that's actually the end, but then we're going to add plus this times this. Now that's going to have the same coefficient, so I can just write it in here. Well, actually, it's easier to think of it. I'm just distributing these to the side. That's a better way to say it. I'm just distributing these to the side. And now we get the second derivative of this, and sorry, this is an x, and y squared pi squared over ly squared. Second derivative of this. Second derivative is going to have a plus sign. I didn't forget about the functions themselves, though, because remember, when we take second derivatives, of course, we still get back the whole function. So give me a second and I'll show you. It goes away, as you'll see, as you just saw here, but squared over LZ squared. Now, of course, when we take the derivatives, what do we actually get? It's this time. It's these things times this whole thing itself again, right? Each term, when I took this d dx squared times psi, I got the second derivative of this whole thing, which equals the second derivative of this times the whole thing, which equals, you get a minus sign because I take two derivatives of the sign to get minus sign, so that's where I've made that plus. Get this, two of these, and then you get the whole thing again. So I should really multiply here psi again. It's the whole psi. Well, this is part of the psi. You'll see that I haven't really rehearsed this. Anyway, let me just erase this. And then this equals e psi, but of course, we can just cancel the si's because they're the same on both sides. This one is, oh, okay, well, I guess I didn't need to write this 8 over v then. So the reason I wrote the 8 over v is because I thought we needed it, but it's still just in this psi, right? Psi is this whole thing. And over here, we still get the same whole thing, right? So now I should literally just have e equals this thing. This is just a big number. This is h bar squared pi squared, so I'm just factoring out common things, over 2m, all times nx squared over lx squared plus ny squared over ly squared plus nz squared over lz squared. Equals e of, and now remember, it's this, of course, the wave function had 3 quantum numbers, so of course this better have 3, and it does. Nx, ny, and z. And so this is just the other part of the solution. Now the difference between this and what's written in the notes, or sorry, on the web page that was sent on the chat, the difference is in equation 20, they literally write this identical thing, but they use, this is the thing I was saying on the, I also said like last week or something, h bar is equal to h over 2 pi, I believe. It's either this or, hold on. I'll move it the other way around. And then I lost my cap. Whatever. Let me look it up. Because I feel like I always get it. I always think, okay, this time I'm going to remember it. And then oh, thank you. Why is this difficult to find? H bar equals h over 2 pi. Yes, okay. And now, therefore, all right, of course. So therefore, 2 pi h bar is equal to h, right? And now if I just, I guess that's probably not the, well, that's fine. Well, no, let me just do it the other way. So therefore, if I replace this h bar squared right here with, right, replace this h bar squared here with h over 4 pi squared. The pi squared is going to cancel, and I'm going to get an 8 on the bottom. So in the notes, it says h squared over 8m, which is literally this in just the other coordinates. Just so you know. So if you're worried why in equation 20 on the web page, which is, again, I keep talking about, it's very good. The book is, you have the book as well. But the web page is very good. But you'll see that they use h. I don't know why. They shouldn't, because the shorthand equation always has h bar. So I would just always use h bar for these. So this is the correct version. But of course, this is still fine if you want to use a little, just regular h. That was the thing I totally forgot to mention last time that I said on the thing, but I'll just say it in person now, which is that h and h bar differ by this. And this is the h that we've been using for like e equals hf or E equals hc over lambda. These are for photons, right? And h is Planck's constant, 6.06 times
626.
something like that, yeah. Times 10 to the negative 34 joule, whatever, seconds. Anyway, that's h. Okay, but h bar, which is here, and, well, it's all around here, is this over 2 pi. So just make sure. Of course, and I said on the last homework, if you did the wrong one, it's fine. But from just make sure you know that we're actually kind of switching conventions because, well, I don't know why. It's kind of silly. Because it seems like even here it would make more sense to do h because there's pi. Like, it looks better with h. Anyway, I don't know. It doesn't make any sense. But, yeah. Okay, so does that make sense? Does everyone see how I got the two results? The only results I wanted to get were the wave functions of a particle in a box, with defined by 3 lengths. It's a square box. Defined by 3 lengths, L, X, L, Y, L, Z. How I got these ends, which kind of came out of nowhere when I did it here, but in the first, I think, last Monday, I think, or whenever my first one was, when I did the infinite square well in 1 dimension, which is the kind of standard example, you saw that the quantization condition, the fact that the wave function had to go to 0 at the ends, meant you had to have like a sine function, kx, and then the fact that it had to, that sine of KL, which is, if this is L, the sine of KL had to be 0, gave you that KL had to be n pi. So remember this whole thing. This is where the quantization comes from. So this we did a bunch of times last semester. This is the same thing. So if you're wondering about like, why am I doing this so quickly? This was last few office hours. It's because this is identical to the one we did last semester. It's not a new thing. If you were worried that, oh, it's a quantum mechanics, everything's different, it's not. This is the same as we got, like this condition we came to all the time. And then we solve for k, and you get n pi over L, and that's n pi over L right here. Okay, just of course replace all this with x's, fill in x's wherever, because there's only one of the dimensions. And the only reason we can separate this, the only reason I could write this as x times y times z and do them as just 3 separate things and everything looks the same, just 3 separate dimensions, the only reason is because this is a separable equation, like this. If I replace this with the potential of, like, let's say it was like a sphere well, like imagine a quantum system where the potential is infinity outside except for inside a sphere. That would be really hard because, well, it wouldn't be, okay, it would be really hard. I think it would still be separable, but it would be separable in a different way. The point is that the reason the V going away, and V, it's not like V was like, kx or something, or I shouldn't use k, lambda x squared. That would be, if this was this would be a nightmare. Like, the reason it's so simple meaning that it just separates into 3 examples of the problem we've done before, is only because everything kind of, like, you can see that the x component completely separates from each other. And in the notes, in some place, and probably in the book, they'll actually write this as 3 separate equations, where they'll write ex, and then they'll write another one as ey psi with the second one, and then ez. You could do that too, that's fine. I just didn't do that because I just did it in a different order. I didn't solve the energies first. But whatever, it's the same thing. And of course, if you do as ex, ey, ez, you know that the actual energy is the sum of those energies, right? Basically what you're saying with the ex is that if I solve for ex here and I forget about the other things, what I'm doing is only finding the energy contributed in the x direction. But of course, energy doesn't have any direction associated with it, so the true energy is just all of those added together. It's just only the x component of the wave function, like they sort of share the energy. Each wave function itself, each part of the wave function has some of the energy, and so you add them all together to get the true energy, which is this, and that's how you can see, of course, I literally just added 3 things together, and each of the 3 things, that is literally the one-dimensional infinite well in the x direction. The second term is literally equal to the one-dimensional. And it's very, very nice. Like, it's nice how it worked out like that. So that's it. Now, okay, so that's fine. Now, the point of the the next things we have to worry about are, it's kind of weird that we have multiple quantum numbers. With the last homework, we had this same well, and basically the last homework was like this, right? Cover this up, and that's the one we had. And they just said, okay, if you have this wave function, n equals whatever n equals, and it can't be 0. We saw it can't be 0 because then the wave function would not be, I erased it, not be normalizable, but that's fine. And it can be 1, 2, 3, etc. Okay, and those are the energies, and we saw O define the transitions between the states, and therefore the wavelengths of the photons that can be emitted or absorbed. We have to find the differences in the energies between those states, and that's relatively simple because it's just there's one number. So only thing we can do is change that number n, right? We could just say, okay, well, I don't know, n equals 3 to n equals 2, just subtract them and you get the difference in energy, and therefore you get the photons that are emitted, the energy of the photons. In this case, we have 3, and we get another problem. It's not a problem. I shouldn't say problem. We get another thing we have to think about called degeneracy. Specifically got this marker because it was working really well. And it stopped working. I've already see they work for like a second. Well, let's just keep going. Okay, so then we get the thing called degeneracy, which is the fact that if I can okay, well, let's just say what's the ground state of this system? The ground state is the one with the lowest energy, and remember. Let me think about something. Okay, whatever. So the ground state is going to be when n is going to be this one. We can write it as E111. And it's going to be when all of the n's are 1. For some reason, I can't remember. The thing I was just thinking about is, why can't we have 2 of them be 0? Oh, because then they would be non-normalizable. Sorry. The reason we couldn't have, if it was one dimension, we couldn't have the n be 0 because then we would have just the flat wave function. And I was thinking, well, we have several, so why can't 2 of them be 0, 1 of them, but then it would still be 0 because we multiply them all together. So anyway. This is the E11 is the lowest value of the n's such that psi 111 is not equal to 0 everywhere. Therefore, it is normalizable. Right. So this is the reason we have to start with 111. Now, if we compute 111, we get okay, just plug in 1, you get like what 3, right? 3 h bar squared pi squared over 2m. Oh, sorry, it's not 3 because, sorry, I forgot about the lengths are different. So it's this number times 1 over, lx squared plus 1 over ly squared plus 1 over lz squared. Obviously, just look at that thing and plug in 1. It's not super intriguing, but anyway, so that's the ground state. So this is the ground state. The only thing that makes it a ground state is that it's the lowest. So it doesn't mean anything like magical or anything. It's not like you have to look it up, or it's literally just means the lowest one. And now, what is the first excited state? So that first excited state just means the next highest energy level. It doesn't mean anything about the n's necessarily. It just means the next highest energy level above the ground state. But of course, it kind of does mean something with the n's because you can see that the next highest E is just going to have something, at least one of them must be 2, right? Now, if I make more than one of them 2, I get something even higher. So clearly one of them has to be 2. So I could write E211. And I'm not going to write out the whole thing. You'll see, you just replace this with a 4, right? Because that's 2 squared, right? Now, of course, so I should also mention that if any 2 of them are the same, the formula becomes a little simpler. If all 3 of them are the same, the formula becomes very simple. But I want to leave it general. And it doesn't matter. Like, it doesn't help. The problem doesn't become any simpler. It's just that the formula becomes simpler, which is not the same thing. The problem is exactly the same. It's just that, it's actually, I think, you know what? Sorry. It's easier to think about when they're all different, I think, because then you can actually see the separation between the things. So let's say E211. So this is called the first excited state. And the energy is some number that's slightly higher than this number. If we had values, we could plug them in and find the actual value. We could find the difference between the two states, and therefore, if a problem said something's in the first excited state of this 3D whatever, and then it dropped to the ground state and a particle, then what would the photon emitted have a wavelength? We could just subtract their energies and then find, using this, find their frequencies or their wavelengths, right? Fine. That's interesting, but, well, it's not very interesting. But there's a problem with this, which is that what about this state, E121? This is not the same exact thing. It seems like, oh, this is the same as this thing, it's just one of them is a 2. But it's not, because in this box, if I say ny is 2, that's actually not the same as nx is 2. You know it's not the same because the lengths could be all different, right? You set up your coordinate system, it means something different. And in this equation, it's not obvious why they're different, because you could just be like, what if I just relabel them or something? Like, is that kind of like a fake doubling? Like, am I just getting 2 because I labeled them like this? Well, let's look at the wave function. Remember, this corresponds to the wave function. This corresponds to psi 211, and this corresponds to psi 121. These are clearly not the same wave function, because this one has a 2 here, the second one has a 2 here, and the first one has a 2 here instead. And that means that if you actually plot it in the x direction, like one of them you get this in all 3 dimensions, and then, the ground state you get that. One of them you get like, what is it, this, right? This is n equals 2, the first excited state for the, so one of them you get this in the x direction, and then this one you get it in the y direction. So those are clearly different, like geometric states. And then of course, there's E112, which is also a different one, right, which is in the z direction. Now, the thing that makes them degenerate, this is not a problem, this doesn't cause any issues. The thing that makes them degenerate is that they have the same value of the energy. We can see if that's clearly true because plug in 2 here, 1, 1, of course it's the same as plugging in 2 here and 1, 1, right? So the thing that makes them degenerate is that the energies are all the same. So let me write it like this. This is like the definition of a degenerate state. And psi 211 is not equal to psi 121, which is not equal to psi 112. Of course, when you do any of these problems, if you were going to set it up, you would have to, I had to write somewhere nx, ny, and z in order. I couldn't just be like you have to know what they mean, y and z. If I switch the order, then 211 doesn't mean anything unless you know that this means nx, ny, and z. So just so we're clear, it's not like this is kind of a standard thing in this problem, but you do have to decide how to label them because it's not obvious. Just looking at this, it's not obvious what I'm talking about. You have to remember the n values for each of the dimensions. Anyway, so these two statements here, if these are true, that means you have a degenerate state. And this is called a triply degenerate state because there's 3 of them. You could have 2 of them be the same, and that'd be one thing too. That'd be doubly degenerate. And so we can also write them as, sometimes they write the states as like 2, 1, 1, 1, 2, 1. These are just notation things. This is not and that's I think how they write them in the web page. And they write the total energy. So the degree of degeneracy is 3 for this one. The degree of degeneracy for the ground state is 1 because it's not degenerate. That's pretty much it. There's another question. So I think this is question 1 and this is question 2. Question 3, I don't remember exactly the numbers, but I believe question 3 then says something about electrons. Maybe it doesn't say electrons. It says something about fermions. So this whole problem, I've been just dealing with wave functions. I never said what the particles were or what it doesn't matter what the particles are. It doesn't matter what we didn't have to use any of the other principles of quantum mechanics that we've been talking about, the Pauli exclusion principle or the or sorry, I meant the Heisenberg uncertainty principle. We didn't have to use any of those. We do now have to use the Pauli exclusion principle. That's what I was trying to get at. The fact that they say electrons, you should know. You shouldn't already. You don't have to already know. You should know now that electrons are examples of fermions. So a fermion is a specific type of particle. I think I mentioned this last time. It has spin 1/2. If you don't know what spin means, that's fine. I don't think anyone in the entire world knows what that means. Anyway, spin 1/2. I'll just list. I think I did this. Did I say this before? Anyway, like the particles that have spin 1/2 that are fermions are quarks, which make up protons and neutrons. That's like the things that make up protons and neutrons. Electrons. I mean, there's more. I can muons, neutrinos. You'll probably only ever have examples where they say the word electron. But you do have to know that when they do this whole system, if they say how many, if they say something about electrons, you now have to know. You should think electrons means Pauli exclusion principle. Is that how you spell it?
Yeah, you're there.
So you have to know this thing. They won't, of course, they won't explicitly say it, but you have to know that as soon as they say it's electrons, if they say something like how many electrons fit, which is what they'll probably say, then you have to know Pauli exclusion principle and that 2 electrons fit per energy level. This has to do with the fact that they're spin 1/2.
Oh,
That's kind of part of it. Spin 1/2 means that in any given quantum state, you can have a spin up and spin down. So there's sort of like the half fill a state. That's not literally what that means, but that's a fine way to think.
So is that kind of what the S level is? Where you have like 2 electrons?
Yes, yes. The reason I'm hesitating is because I don't remember what the S level was. But I think
and then P has 6.
Oh, no.
Do you know? So
Oh, yes, he is. Okay, yes. Okay, I'll talk about that after I do this problem.
Okay.
Yes, that's for the shells for an atom,
Oh.
which is basically this problem, but just different quantum numbers, which are not. I'll get to that.
Okay.
Thank you for bringing that up because I do need to talk about that. I'll remind myself. SPDF. That's what they're called, right? Okay. Okay. So now, if they say how many, so here's the quantum states. I'm gonna have to erase something. I'll erase this side because I kind of like. I mean, we're done with it, but all right, I'll erase this side. Okay, so that's all the actual answers. But now that they say, what about when we put things in it, like electrons? Then we have to start. Let's do like the graphical representation where we put the energy on the vertical axis. This is the thing where this doesn't mean anything. I'm just gonna like stack the energy levels. So here's energy. This is energy is 0, and which nothing. Remember, with this we can't have energy be 0 because that would mean that the wave functions are flat everywhere, which can't happen because they're not normalizable. So this is ground state. Sorry, I shouldn't write ground state. I should write E111. And then for the first excited state, we have, I'm going to draw it like this, 3 separate things. So this is E211, E121, E112. And the reason I'm drawing with the same, well, I'm not really drawing with the same, the reason I'm trying to draw with the same level in the vertical axis is because they're at the same energies. This is the whole point of the degeneracy. Then the next one, so now let's actually keep going a little bit because in the problem I think they say something about 12 electrons, which is a lot, and they're not all going to fit. Is that what they say, electrons?
That's the next problem.
Oh, okay, good.
But the first one says how many electrons can each of these energy levels have?
Oh, yes, okay. All right, well.
So that would be this one that you're doing now.
Yeah, so how many, so by the fact that there's 2 per energy level, which is because there's spin 1/2, we know that how many can fit in here, and it's exactly 2.
Yeah.
Right, so how many can fit in this one? There's 2 electrons. Actually, how I would...
So then the second level, E112, wouldn't work with the equation? Because there's a 4 in the Z. What doesn't have to be 1 in the very last one, so then only 4 electrons can fit in the second energy level.
No, you could fit 6. Because each of these states, there's 3 wave functions, 3 possible quantum states, and 2 can fit in each. So you're saying something about the Z is special?
Yeah, I'm just, when I do all the equations, the one equation wouldn't match up with the other 2. Because one would be 9e, or h hat squared pi squared over 2.
Oh, you're doing the actual problem where it has
Yeah.
x and... Oh, okay. Let's do...
Are you just talking in general?
Sorry.
Do you get what I'm
2,
saying
1, 1
there?
is equal to
So,
1, 2, 1.
Yes.
so yeah, the
Not
first,
1, 1, 2. So you've only got 2 energy levels.
Yes, you're right.
Yeah,
You've
so
got-
that's
you've
why
only
you
got
don't-
2.
I'm sorry. Okay, I've made a small mistake.
so that's
It's
why
a-
you'll only be able to fit 4 electrons
You're
in the
right.
second level. Where if it was all the same thing, you could fit 6.
Yes, exactly.
Okay.
I'm sorry. So I've made a small mistake when I've written here. I've assumed through this section, starting here, I've assumed that this was true. Okay. Which is just saying that I assumed it's a cube.
Yeah.
Right, because of course, as you pointed out correctly, that if you plug in different values for these, it doesn't always add up to the same because these values might be different.
Yeah.
So you could have a different L, and that would make the energy levels not be the same anymore. So that's an excellent point. So let me...
So your whole thing would make sense at each energy level, depending on how many equations you could write,
Yes.
could fit more.
Let me do the whole thing where they're all the same,
And
and then I'll go back to where they're
Okay.
not the same, because the reason I know on the homework, 2 of them are the same,
Yeah.
but
so
the thing is, depending on what the third one is, it's not obvious whether it's going to be higher or lower.
Okay.
So it's a little hard to do in general. But
Okay.
I'll come back to that.
Okay.
Yeah.
Thank you.
So let
Makes so
me
much sense.
redo this. This is going to be a 3 now, and this is 1 over L squared. This is going to be equal to L. Okay, so from just for this example, L is going to be I'm defining L to be just equal to the length of all 3, which are now the same.
Yeah.
Okay. Now these are the same. If L, X, and Ly were different, these energies would not be equal. Does that make sense?
Yeah.
These 2 specifically, L, X, and Y were, and then the problem, Z is different, so therefore this one is not the same as. So I'm just saying this for myself. Everyone else knows it. Figured this out before I did. So anyway, this is just it's a special case where they're all the same. I just want to show you because it's easier to draw because I don't have to do any calculations. If we do this whole thing, now everything I said is true, and now we do have these 3 energy levels here. Now the next one, though, let's just do the next one. Well, right above this, what's going to be the next energy level? Well, we're going to have what if I'm going to need to make another one at 2, right? Now, actually, if we look, it's not. Sorry. That's what I meant to write.
Yeah.
Now it's this because they all combine over the same. Yeah. Now it's actually not clear. We'd have to look at the numbers. It's not clear whether I could do this E311, but I could also do E221.
Yeah.
Right. Those are I don't actually know which is higher. I mean I do, but I don't know right away. I actually have to compute them, and so 311 is going to have 9, 10, 11 up here. So it's going to be 11 times 3h bar, blah, blah, blah. And this is going to be 4 plus 4 is 8, plus this is 9. So this is actually going to be a little lower. So you can see how, so E11 is going to be, okay, so if I want to draw these to scale, which you don't have to do, but let's just say I wanted to, this is 1 unit. E211 and this is only, again, in the case where they're all the same, is going to be, well, this is going to be 4, 5, 6. So it's going to be 6 times, okay, well, I'm not going to be able to draw the scale. This is going to be like 6 times higher than this, right? And then the next one, okay, I'm not drawing it to scale anymore. The next one's going to be 221 E 122 E 212, right? We know that those are all the same because, again, it's just by symmetry. You can see that they're all going to be the same in this case. And we didn't know for sure until we actually literally have to try it that 311 is not going to be, you don't know if 311 is going to be bigger or smaller. Turns out that if you do it, you'll get that it is. And so then we'll get E311, E131, etc. You'll see, right? So that, and then now if we wanted to put electrons in this system, we would just say, well, each energy level has 2 electrons, and how I would normally write this is, and like you can write it like that, an up and a down, because each electron has a spin up or a spin down in these states, and so if you just write an up and a down, I don't know, that's what people do. So just write an up and down. So there's 2 here, and how many can fit here? Well, obviously just 6, right? Because 3 can fit in each state. Not in energy. So I shouldn't say energy level.
Used it twice, yeah. You said energy level.
Per state.
Yeah.
Where else did I write that somewhere?
No, you said it.
Oh, I said it. So I'm sorry. Oh, God, this is a nightmare. Okay, 2 electrons fit per state.
Thank you.
Therefore, 6 are in this energy level. 2 are in here. 6 are going to be in here. There's some more. The next one that has more than, and then there's 222, which is even higher. 222 has 1 because, of course, switching doesn't mean anything to switch 2 and 2, right? So 222 there were 2 electrons because it has 1 state. The next one that has more than, that's more interesting than this, is 321. So in E321, well, oh yeah, this is a good one. So E321 is equal to E312, which is equal to E123, which is equal to E132, which is equal to E231, which is equal to E.
That's okay. I was going to ask you that.
Yes.
How do you get more than 3 states?
Like that.
There you go.
So I believe that's the most you can have. You can never have more than 6 states because there's only 3. It's
I thought F could have 14 electrons.
Oh, that's a different system.
Oh, Jesus.
Yeah. So I reminded myself, so everyone's way ahead of me on everything, but I was getting, this is, I'll talk about in a second, where this is a different set of quantum numbers give you this. So this is actually the L quantum number. There's N, L, M, and then there's this other one for spin. There's like, well, I don't know, whatever, doesn't matter. The point is that these are quantum numbers for a different system, which is the Coulomb system, which is the atom, hydrogen atom. These are quantum numbers for a square well. Well, okay, whatever. Just trying to think if you can get more. It doesn't matter. There's no point. The point is that that you can only have this degeneracy when they're the same. Now we could break this degeneracy, or just go to a system where we don't have the degeneracy. If we just say that, I'm going to say this is equal to L, and then we're going to have another thing called LZ. Well, now we'll have this. LZ squared. Now we'll still have some degeneracy because NX, so now I'm going to erase all this. So now I'm going to the system where instead of all 3 levels being identical, instead of all 3 lengths of the box being identical, there are 2 of the lengths of the box are identical, and the third one is a different length. Now I get this as my energy, and I still have the degeneracy because E211 is equal to E121, right? But E112 is not the same as these because, of course, if we put the 2 here, then it's going to be sort of scaled by a different number here. It's not going to be related. If we switch the 1 and the 2 in here, this number is going to be the same. But if we switch a 1 and a 2 like here, the whole thing's not going to be the same. Does that make sense? If they're all different, which is what I was originally writing, there is no degeneracy at all. There could be by like chance, but it would not be anything nice. You would never, it's not gonna happen. You're never gonna see it. So, so if they're all different, you would not have any degeneracy. They would all be different because you could just scale the boxes by different lengths, and each of them have an energy that depends on L. So this is a twofold degeneracy. Degeneracy. That says degeneracy. And then this is another thing that has nothing to do with the other ones. Right? It's another state. Now, I don't want to draw it because I don't know whether this is bigger or smaller than these. You could figure it out if you're given numbers. You have to be given at least the lengths of these, and you are in the problem. You're given that this is like half of these. So given that fact, you should be able to kind of do it in your head. I don't want to do it because I'm going to get it wrong and it's going to be embarrassing. But just if you knew some numbers about these, or at least the ratios, you should be able to figure out just using this equation which one's higher or lower, but you wouldn't know how much, and it would just be a whole thing. So the point is that you get this degeneracy. Now, how many can fit in this state? And now, actually, so I should mention another reason I don't want to draw it is because the ground state is still 1, 1, 1, but I don't even know whether this is the first excited state or whether this is the first excited state. I shouldn't even call these the excited states. This is a state, and this is a state. I don't know whether this is the first excited state or this is the first excited state because I don't know which one's lower. So, but anyway, the point is that if you that how many electrons can fit in this state, you're right, it's 4, right? Because there's 2 states, they have the same energy, and 2 electrons can fit in each state. I'll just edit it out so it looks like I said this whole time. No, but 2 electrons can fit in each of these states, and then 2 can fit in this. So in this one degenerate state, there's 4 electrons. In this one, there's 2. Maybe it's higher or lower. I do know that E311, well, sorry. Then I have something like E221. That's lower than 3. We just showed it's lower than 311. Yeah? And this is the only one because we can't,
Yeah.
if we flip the 2 and the 2, it
So
doesn't
that
mean
would
anything.
only have 2 electrons.
This would only have 2, exactly. So psi, I should say psi, this doesn't make any notational sense, but just pretend that. So psi 221 is the only state in that energy level, because I can't replace the 2 and the 1 with anything because it's not the same. I guess that's it. And then you could have 311, which is the same as 131, which would just be like this. Those would be degenerates. There'd be 4 states there. I'm just trying to think if you could have 2 states, 4 electrons. I'm trying to think if you could have ever more than 2 states, the same energy level with this system. I don't think you could. I think that would be the max.
Yeah.
Because you could only switch
Switch
2,
two
right?
of the
Yeah. So I
numbers.
think it would just be you can only have 2 states per level. You can only have 2 energies with different quantum numbers that equal each other with this twofold degeneracy. I guess that's the big thing. There's a max twofold degeneracy here. Now, if they were all different, as I said, there would be no degeneracy. You just have separate states. You'd have to compute them all separately. You have no idea whether if they're all separate, you have no idea whether like 211 or 121 or 112. You have no idea which one is higher or lower. They're in some order. They can't be the same because otherwise they'd be degenerate. But you'd have to know LX and LY and LZ. So there'd be no degeneracy there if they were all different. There's only degeneracy because the box has some 2 axes that are symmetric, that are the same length. Okay, does that answer all the questions about this? Is anyone still confused by something that I said that was incorrect?
Not by
So
something
also
you
going
said.
on
Okay.
to this problem.
Yeah, and then I'll talk about this one too.
So that's kind of different.
Yes.
So it says, find the frequency and wavelength of the 3 lowest energy photons that would allow excitation or in the system. So how many levels can you jump? 'Cause
As many as you want.
Okay, so
Yeah,
it's
so-
not limited. So you basically would take E5 minus E4 and find the lowest of all the different variations,
Yeah. So
and then calculate
sorry. They asked what the lowest energy photon is.
the 3
The 3
lowest.
Three
So we
lowest
would
energy
take
photons.
yes.
Oh,
So we
so
would
the 3
subtract the E's and find the lowest of those, and then find the frequency based on the lowest of those.
Yes, what I would do for that problem is work out E, just work out E, NX, NY, and Z for the N's are like 1 and 2 and maybe 3. Maybe 1 and 2.
So we were supposed to do from
all the
first
ones.
5.
Oh,
So
then,
it's the same problem. So we already have them,
oh, good.
but
good,
we
good.
would just subtract
yes.
like 5 minus 4, 5 minus 3, 5 minus 2, and find
Exactly.
the lowest of all of them, and then compute the frequency and wavelength from this.
Yes, exactly.
Okay.
Yes. But of course, you
Okay.
don't know, like, again, with just arbitrary numbers, you don't know whether going from this state to this state
Exactly.
is lower than going from 311 to this state, right? You don't, or anyway, whatever. You
Yeah.
know what I mean? You don't know because there could be any numbers, you could adjust them.
Okay.
They could be very close to being degenerate, and therefore you could have a very low
Well,
energy
that's
photon.
why you couldn't draw the scale.
Exactly, or they could be very far apart, where maybe the 311 to the 211 is actually the lowest energy state. I don't know, whatever. You
Okay,
could have-
so you could jump from E5 to E1, or
yeah,
from
and
the
you
fifth
could
to
go
the
from
ground.
any number to any other number. Yeah,
Got it. Okay, if you
So
have enough
basically
energy.
just go crazy, like
you go crazy.
counting them.
I mean, hopefully because
Find
you've
the
written them
lowest.
out in the previous problem, you should be able to see if two of them look very
Yeah.
close to each other.
The
I mean, yeah, you don't have to like write like a MATLAB program to test all the. You can just if you get it wrong,
Couldn't
it's not a
see
big
that.
deal.
Not an option anyway.
As long as you wrote them all out, that's like I don't. This is a little bit silly. They should
Yeah.
just ask you the lowest. They shouldn't ask you the 3 lowest. It's kind of silly. But just remember that how you get the energy is you do N, X, N, Y, and Z to, NX prime, NY prime, and Z prime. Like this is the whole thing. All of these, every photon comes from a transition from this to this. The energy is given by E of this minus E of this, or
Yeah.
what the other way around, or whatever. Either way. Like you could, because
Because
one
you
would be
could go
absorbing.
up, or, yeah.
Yeah, one would be absorbing, one would be
One
emitting.
comes
Exactly.
yeah.
out
So,
to 4.
Okay.
So it's like
but this is how you say every transition of this system looks like this.
when
Yeah.
They don't have to all be different either. Of course, NX can be NX prime. That's fine. But
Got it. Is it weird I understand this more than I understand last semester?
no,
Okay.
it's not
Whatever
weird.
you plug in.
I'm glad
After you switch.
because last semester
This
had
is
a
more
bunch of.
chemistry, though.
Yeah, exactly. You might have seen some of this, especially with this.
Yeah, definitely.
You're used to
that
these
part
energy
is-
levels, and
This.
last semester was like a bunch of stuff all at once that we didn't really go into at all.
Mhm.
And this we're spending, like you're spending what 3 weeks now on quantum mechanics. Like it's
Yeah.
kind of like you're spending all on the same thing. So, which I kind of wish they did the whole time, but like maybe get rid of some topics last semester and just spend more time on the few topics that you did. But anyway, so
So number 5.
Yeah.
It says what photon wavelength would cause the 4's easy.
Oh, okay then.
Sorry, I can show you
Go
my
ahead.
book. So number 5, I found an equation online that I think is the same.
Uh-huh.
Like I didn't get where he. So the equation in the book, I guess, is telling you to use E equals m cubed. So here, let me show you. This.
Yeah.
I'm on the last one.
So this is the problem.
oh, in hydrogen, yes.
Yes. So, I found the Rydberg
Yes.
constant for
Yep,
hydrogen.
yep.
Now that's not in the book.
Percent.
So this is the equation you would have.
That
to,
is the correct equation, though.
Okay, so
Rydberg,
it's R. Yeah.
something like that. When was I
Yeah,
asking
that's
you about
exactly
this last
how.
time?
Yeah.
I was asking if you remember a ride. Did I say this Rydberg?
Nope.
Okay, never mind.
So it's they abbreviate it online.
I was thinking of it and I didn't remember the name. I must have
Okay.
been because I was asking
Oh,
you if you
yeah.
remembered, and then I couldn't remember the name, so it was a disaster.
We
But
just went on past it.
yeah, the ride. There's a constant times 1 over n squared.
Do you remember you talking
For this
Well,
is for
minus-
hydrogen.
Yeah. Well, minus so initial versus final.
Oh, sure. Yeah, for a transition. Yeah.
Yeah.
So
Okay, because I found that online and it's not in the book, or at least I couldn't find it in this chapter. But I would assume you were supposed to
Not
use
surprised.
this equation, but I couldn't figure out what Q was. So I didn't know where Q was, and I couldn't find it online, and that's what I found instead of using this. So that's what I did, but
that equation. Okay, I don't recognize that equation except for the right side is definitely correct.
so then where would you get N2 from in this situation?
So that okay here. I'll go through it a little bit from behind what you said, but I'll answer your question.
Okay, so
So-
because that's right then.
Yes. So when the whole Schrodinger equation we just solved, I'm not going to solve it for a hydrogen atom, but remember it's the same process as all. It's the same process as every quantum mechanics problem, which I said is you start with a potential and you go to psi and E. And of course, you need some quantum numbers that come along with it. So again, just like every quantum mechanics problem we're doing this, how you do it is with spherical coordinates. As I said last time, those are very difficult, and the Laplacian is crazy. The point is you get psi with n, l, and m, which are 3 quantum numbers. They have an r part and then a part that, remember I said is called a spherical harmonic. It's not important. Don't worry about it. But that's this L is where you get. So these are quantum numbers.
So R is just the 13.6
N, L.
No.
converted to joules per second.
Are you asking about 13.6?
No, because it's the R constant is in meters, correct?
No, this
The
this
log.
I'll get to this in a
Okay,
second.
so
This
that-
is the answer for the energy. Let me erase this for now.
So that doesn't.
But it's just 13.6 times the other half of that equation equals the HC over wavelength.
Oh,
right?
for photons?
Yeah.
Yeah, let's just do the energy levels of the atom first, because I just want to show you where this comes from.
Okay.
I'm not going to actually do it, but I'll just tell you where it comes from. So it's the same exact process that we just did.
Mhm.
We get an E, we get a psi NLM. The N tells you the principal energy level, N equals 1, N equals 2 of the shells of a hydrogen atom. L tells you the specific shape. L and M both tell you the shape of the orbitals. So that's why they're called the spherical harmonics, because they're only defined on the sphere. They're not, N is defined as from the radius. That's why the bigger shells are farther away. But the L and M tell you about the shape. L
It's just plugging.
can be 0, 1, 2, all the way up to N. And the 0, 1 is called S. The 1 is called L. The 1 is called P. The 2 is called D. And the 3 is called F. And then they go on. So this is from chemistry. In chemistry, they use SPDF. In physics, you would just use 0, 1, 2, 3. In the N equals 1, that's why you only have an S level, is because you can only go up to, actually it's like N minus 1, I think. Doesn't really matter. And then this goes from 0, actually it goes from negative L to L, and this has to do with the spin. So basically this means that like for each L level you can have 2 electrons with up and down states. So this is all part of that. You don't need to know the derivation of any of this. I'm just showing you that this is identical to the state thing we just did, except the quantum numbers are not like 3 like X, Y, Z, where they're pretty easy to imagine. They're very hard to imagine. And you can look up pictures, and if you look at pictures of the orbitals, they look complicated. They're literally just solutions to the Schrodinger, the same equation, just in a really complicated coordinate system. But it's the same exact solution. In fact, the potential actually looks pretty simple. Right? It doesn't look that crazy. It's not like a weird function. But yet, for some reason, you get this thing. The next cool thing, which actually makes it easier than the box, is that the energy levels, of course, are still defined by 3 quantum numbers, but it turns out that they actually don't depend on L and M at all. And that has to do with the fact that N is the one that tells you about the radius, and the radius is the only thing that appears here. So therefore, the N, the principal quantum number, the energy shell level, tells you about the energy. And remember, in the last one, we just had h bar squared, pi squared over whatever. Now, for this system in general, you'd still have all those constants, and it would look really weird. But because we know that this is a hydrogen atom, we know what M is, and we can just plug in h bar. We can just plug in all those numbers, and if you just plug in all those numbers, you get this. If you don't plug in all those numbers, you get a very complicated formula with q's to the 4th and all these crazy things. So you get this. This is the energy for the nth, for a particle, an electron, in the nth energy level with any L and M of a hydrogen atom. Now, if you want to find, now we're done, except they're asking you about transitions, because
Yes.
that's very common. Transitions are just E N1 to En2.
Correct.
And therefore, energy level of N1 is just given by, and energy level of N2 is given by this with N2, and so to find the actual,
So that'll give you the same thing as the constant one.
this is the constant, yeah, the constant that
That I
should
have.
just be equal to this.
Okay.
Okay. So this is exactly, sorry, I had many thoughts entered my mouth at the same time, but, so does everyone see that this is the same? If your question is about the minus sign, I'll talk about that in 1 second. But does everyone see that this is the same, what do you call it? Intuitive process as we just did with the box. There's just no new concepts. The equations look very different. There's very different weird things that don't appear in places, and there's a number. Where did that come from? All that matters is that we did the identical process. It's just I didn't show you how to do the differential equation because I don't really know. Again, like no one really knows. Someone from like 1920 did it once, and everyone else has copied it. So anyway, actually, like Gauss did it in like 18 something. Gauss is something weird on that. It's like a bit of a racer. Anyway,
Jesus.
that was really gross. Anyway, so that's all that. Now, it just happens to be that when we do for a hydrogen atom, we don't have things like, oh, it's a quantum box. And it's like, okay, well, you just got to tell me the length, because I don't know how big a quantum box is. In this case, it's hydrogen. We know about all the lengths. We know about the mass of the proton. We know about the mass of the electron. We know about all that stuff, so we can just compute that constant out front, that m h bar squared, n squared, pi squared, whatever it's called. We can compute that, we get this. Now, there's one subtlety, which is that it's a negative number. In all the other cases, we had positive numbers. The reason is because they define, because this, if the potential is negative, so what they want to do is just say the potential looks like this, and this line here where it like goes to infinity is equals 0. So every state has a negative energy. That's the only thing. Because remember, just like with potential energy, you could just say that it's potential energy of a regular object is mgh. You can just set h equals 0 wherever you want. You could set it to be at like the highest point of the roller coaster or whatever, and everything would just be negative, but it's fine. It'll still work. The reason they do it this way is I don't actually know. Well, actually, no. A good reason is because the potential actually does go to infinity. So it'd be like, well, where do you set 0 at, right? Like it goes forever. So like, there's nowhere to set 0. So they just set it at the max, which is where the energy approaches. And E equals 0 actually corresponds to a free electron that's not bound to an atom. So that you can kind of see, when does this go to 0? Well, that's kind of when this goes to infinity. It's kind of a weird thing. But it just means, it's called ionization, right? When an electron leaves an atom. So if you give it enough energy, it turns out if you give an electron in the lowest state, in the n equals 1 state, if you give an electron positive 13.6 electron volts, it will leave the atom. And that's where this number comes from. I mean, it comes from the equation, but it also matches the experimental fact that the every electron has has what's called an ionization energy of every electron in the lowest possible state, which just means n equals 1 of any atom. If you give it 13.6 electron volts, it will be completely free and have 0 extra energy. So this is the most you could get. So if you go from 13.6 EV and you convert that to like lambda for a photon, that's the most. Sorry, that's the lowest lambda. Let me stop saying lambda. Let me say go to energy of a photon. That's the highest energy photon you could ever get out of any atom, because they can't possibly have any more energy than this. That's one of the reasons they set this to be 0, is because it's like the most. Because it's essentially going from the n equals 1 state, which is the lowest, to the n equals infinity state, which is the highest. And I'm sorry, just one more thing. As always, there isn't a largest value of n. Just like in the square well, we never really talked about it, but technically they go to infinity. Like, you can have an infinitely, like, you can have it. It's possible. In this case, it actually does make a little sense to talk about because you can have electrons leave the potential completely. In the square well, it's a little weird because you just have to stuff infinite amount of energy in a box. But this case, it's not a box. Nothing's trapping it. It just has zero energy outside. So you could ionize an atom by giving it this ionization energy here, or the Rydberg energy, whatever it's called, which is just this. But of course, generally, the questions will ask you about transitioning from energy levels. And again, we don't have to worry at all about L and M, which are kind of the hard parts. At least, I think, in chemistry, those are the hard parts. Of figuring out the shapes and the solutions and what they look like and how many you can fit and all that stuff. That's, I guess you could look all that stuff up. But the thing about the energy is that it's only dependent on the n. So transitions are just this formula. Okay.
So, is it just notation? They have a line under the N? Is that just...
Oh, yeah, that's probably notation.
Okay.
Yes. Yeah, they have a line under all of the things for some
So
reason.
N does too. I guess
Yeah.
that would be N. Yeah.
I don't know why.
Oh, N equals this, which is just...
Yeah.
Actually,
Let me... Because they start, even M has it here.
Hydrogen and all states are the same value of N. The same energy. I have no idea.
That's very strange, because I see that they have M underlined, which makes sense, because M is this, but it's also the mass. So,
Yeah.
But I don't know why
Oh,
N would be.
Yeah, I don't know either. Okay.
Anyway, that's, yeah.
Cool.
They have a line under it, but... So these are just two examples of a quantum mechanical system. These are just, all they are is two examples of the solution of the Schrodinger equation, which is just a differential equation, with two different potentials. One of them is like a box, and one of them is like this 1/r. But of course, theoretically, someone could just give you any random potential, and it would be completely a different system. It would look totally different. The energy levels would be really weird, and they're not usually very useful because hydrogen is all around us, and boxes are simple. But every other example is kind of silly. But except the harmonic oscillator, which is kind of cool, but we're not going to do that in class, so I won't do it. But
Did you talk about 9.9 yet?
what was
It's
9?
on the bot. It's on the board.
Oh, yes. I wrote it so I wouldn't forget it. Yeah, so 9.9 was kind of, I did it a little bit last time in the I think it was in the beginning of my last office hours. So I won't go through the whole thing again, but I'll just mention that they set it up slightly differently. So the problem is about the finite square well. And they set it to be minus L naught and L naught. Now, I think I set it to be 0 and L, or 0 and A or something. I mean, of course, they should be identical, right? It doesn't matter where you set what you put your x-axis coordinate system on, but whatever. I know the people in the video don't like red but they're gonna have to suck it up. I mean, they're gonna have to buy me black markers. I think is the solution. They don't work.
Okay.
Oh wait, what do you mean?
I don't know, there's like a whole
Oh, those yeah, no, they don't work. I thought you meant this is because I found a marker that was working beautifully until like 10 seconds into it and then it stopped.
Wonderful.
No, those definitely don't work because I just tried them all and put them over there. Anyway, so they want you to find the first three wave functions, and they give you a hint or something that two of them are even, one of them's odd. And now it's going to be slightly different in the appearance from what I did last time. So the reason is because they set them to be like this. That means that, of course, if I shift this whole thing to start at 0, we might get different like cosine and sine might switch places or whatever. Of course, none of that should matter. It should be just as simple, but whatever. And so the point is that we start with 1, 2, and 3. These are the 3 regions. The Schrodinger equation is solved in all of them. The energy is 0 in 1 and 3. So, sorry, the potential is 0 in 1 and 3. So if we, again, I'm not going to write the whole thing again, but I'll just outline you the method to solve it. We solve the Schrodinger equation in 1 and 3 with, it's just a free particle. So it should look like, sorry. I meant to write E. Let me use a different marker, actually. Okay, so my particle has energy E. My potential, that's fine, I guess. My particle has energy E. My potential looks like this. The energy is less than the potential in 1 and 3. And we know from all the solutions I did that that means that the wave function is going to be like e to the kx plus e to the minus kx. So remember, they're real numbers here because the solution actually has i's in them. But if this number is negative, then you remember that k gives you an I under the square root, and we get another I, and therefore it's negative. That's all a lot of words, but if you don't remember that, I explained it in the video. I hope
In which
very
one?
well. I believe it's the
One's-
the most recent one.
Okay.
I think at the beginning. I think. And basically, you get this equation where k has something that has like e minus v in it. Sorry, in this case, it's just v is 0. But then here you get, this is minus v naught is the depth of the well. It's minus because I just want to call this top one energy 0. V equals 0 up here. But the reason I want to do that is because I want 1 and 3 to be like, have no potential, so I don't have to worry about it. So I get this k, and so this is in region 1. In region 3, it's identical to region 1 because it's the same system. So I remember I used F and G, right? And in region 2, the energy is higher than the potential. And so I got something, region 2, I got something that looked like C e to the I kx plus D e to the minus I kx, right? It's I now because I didn't get the extra I that comes from the, in the Schrodinger equation I have like E minus V, and I switched the thing to make everything positive. And if I make everything there positive, so everything in K is a positive number, I could take all the i's out and I get an extra I in this case, but I don't get it here because it's a free particle. So this looks like a free particle because really this is a free particle. It has energy higher than the potential it's in. That means it's a free particle. This is really K prime, I should say. It's not the same K because remember K has that like E minus V in it kind of thing. And in here, there's no V, so it would be slightly different. And now I just have to match the boundary conditions, but the thing that they want you to, the hint he's using says that we should use, I'll erase all this now. The hint is that we should switch our psi2 equation so that instead of showing that I, we could write it in terms of sines and cosines. Of course, you could always do that. It's actually going to make it a little easier because then we don't have any imaginary exponentials. So I'm going to say psi2 is going to be C sine k prime x plus D cosine k prime x. Now, just keep in mind that it's not the same C and D as this. As in, it's not like a one-to-one correspondence. Yeah, it's not. It's like C plus D and C minus D. Whatever, it doesn't matter. I'm just choosing new variables. So I'm going to erase psi2 now because I have psi2 written. Okay, so everyone see how I got psi in the 3 regions? And then psi2 is, like I showed, you can always write it like this or in the other way. The book seems to prefer the imaginary exponential way, but then his hint says that we should then transition to this. So just trying to follow the same pattern of you always write the imaginary exponentials if you can. See if the I cancels, which they do here. And if they don't, then you can write it like this. And now the reason, okay, so now we have to use the boundary conditions. And we know that, remember the boundary condition that was not stated explicitly anywhere, it seems? Well, it's probably in the book somewhere, but that was the boundary condition we need to care about in 1 and 3 is that at infinity, the wave function must go to 0. And we know that's true because there's 2 terms in here, and if we go to negative infinity, if we go to x equals negative infinity, what's going to happen to this term? Negative infinity is going to give us e to the plus big number. That's going to shoot off like really high, and there's no way we're going to be able to integrate it to get 1. It's going to go to infinity. So this term can't exist here at all. In the same exact way, this term can't exist here at all. The f is kx, because as x goes to positive infinity in region 3, this, no matter what f is, even if it's really small, it's still going to go up and shoot up to positive infinity, and then when I take the integral, I can't get a finite number. It's going to be infinity. So in other words, psi 3 has to have just a negative kx. Basically, a way to visually see this is that I know that psi 3 has to go down to 0, and I know that psi 1 also has to go down to 0. There's the alternative, which is this term, is that it goes up to infinity, and that doesn't make any sense. So now I have psi 1 and psi 3 have just some positive number value here and here. And I need to find, now I need to use the boundary condition of psi 1 is equal to psi 2 at negative L naught, and psi 2 is equal to psi 3 at, all right, that's psi 1 at negative L naught is equal to psi 2 at negative L naught, and psi 2 at positive L naught is equal to psi 3 at positive L naught. Right, those are just the boundary conditions. Now, I don't want to do them all because it's just excruciating how annoying. Like remember before when I did the problem, I set one side to be at 0. That's very nice because when we plug in 0, this goes away. And some of these trig functions become much simpler when we plug in 0. When we plug in L naught, nothing becomes simpler. You get a crazy looking thing with constants. It's just a number, but it looks crazy. So I'm not going to actually plug them in because it'll just be a mess of algebra. But you can kind of see that just this, plug in, this is psi 2, and that's psi 1, just plug it in and you can find some relations. That's step 1 where you set up the algebra. I think, and then one of them is step 2 where you actually solve it, and that's just going to be a bunch of more algebra. But what was I going to say about? Oh, right. I was going to mention the thinking part, which is that when you want to find the first 3 wave functions. Now, when they say first 3, well, what are they talking about first 3? Like, we already found that these go to 0. There's no other solution where they don't go to 0, right? But we know that in the middle, these are boundary conditions. We know that the value is not 0. Oh, okay, well, yeah, I mean, it's just not going to look pretty. We're going to get quantization conditions that look like k L naught is equal to n pi or whatever. Remember this thing? Where we have to say something is 0. It's going to be really messy, but we're going to get something like this. And basically, and I'll visually draw it because this is the important part. The lowest one is going to be like this. Because the lowest one has to look like sine and cosine somehow. But it also has to, but it has to have the lowest values of the n's, which is going to be an n here and an n here. And so this is going to be the lowest wave function here. The second one, this is even. It's even because around 0, if you reflect it, you get the same thing. So it's an even one. The second one is going to be this. So this is just like the harmonics of the string, wave on a string. And then the third one, I think, is going to be like that. So 1, 2, 3. And then the point of this, and now to actually explicitly find the functions that, wow, that looks horrible. Anyway, whatever, you see what I mean. They're exactly the same for the string. I know I've said this 100 times. Guitar, string, find the harmonics. It's a one-dimensional problem. The reason that this is so much more difficult in algebra, not in conceptually, but in algebra, is because they set up minus L and L, and it's also not 0 at the ends. It's some weird function like that. But it's the same principle. And the point is that when they say the first 3, we get the first 3. They must have the lowest energy because they have the lowest n value. Because remember, n tells you the number of nodes and antinodes. So these are clearly the lowest 3. But they also mentioned that there's 2 even and 1 odd, and we can see that the lowest one, this one, is even because we reflect it and it's the same. This third one, which goes like this, is also even, right? Because if we reflect it around here, there's a lump here and a lump here, and it goes down in the middle, and if we reflect it, it's the same. The second one is this one that goes up and then down. That's actually odd. You can actually kind of see it looks like a cosine, and this looks like a sine, and this looks like another cosine. That's probably what it's going to be. You can probably look this up on Wikipedia, by the way, if you want the actual answers. Anyway, and then again, so the point is that just like when we, just like when we did the guitar string, we get the lowest one is around the center, it's sort of symmetric, and then we get the next one is anti-symmetric, meaning around the center, if you flip it, you have to mirror it upside down. So this is symmetric, this is anti-symmetric, this is symmetric again, so these are just cosines and these are sines. So I shouldn't say symmetric and anti-symmetric, I should say even and odd. That's the literal mathematical names for them. And that's the whole point, is that that's the only point you get those things. It's just really annoying boundary conditions in this problem, but if you look up finite square, this is called, I'll write the name. This is not called hydrogen. This is called the finite square well. Finite because the potential doesn't go, it's not like these are infinite walls, and we know it's also finite, we know it's different than the finite one because the wave function doesn't go to 0 immediately, it decays to 0, right, as you get outside, because at this point, the energy is actually, the potential actually has more energy than the particle does, than the wave function does, so it decays to 0, obviously dependent on the difference in energy. Now, if you can imagine, let's say we had this wave function in this state, and it's just sitting there, and we drilled a hole right here, so like this, and we put another well here, this wave function is not going to be equal to 0 right here. It's going to be like this. There's going to be some amount. So this is the tunneling. The fact that if you, now just like with any wave function, if you just take a region, I'll call this A to B. If you take this wave function, which the other reason I didn't solve is because it's going to be messy. It's just a wave function. We take that, we take the integral of that wave function squared from A to B. It's going to be psi 3, it turns out. It's the same one, but it's just the third part. This is not 0. This means that there's a probability of, this literally means that there's a probability of finding this wave function, this particle, between A and B. So this is tunneling. This is the example of tunneling. If this was equal to 0, there would be no tunneling. And if you take the wave function and you take the limit as m goes to infinity, you would get that this, not infinity, but m goes to very large, let's say, like a person or I don't know, yeah, person, whatever. Then you would see that this third part here would actually go like plummet to 0 like that. It'd still be an exponential, but it would be a very, very sharp exponential, and then this integral would be very close to 0. So that's literally the explanation. What I just said is literally the explanation of why people don't tunnel like quantum objects. It's not because the rule doesn't apply. It's because the rule does apply, and the probability is very small because this exponential decay on both sides, it's effectively like an infinite barrier. So to a person, a wall is effectively an infinite square well, where the walls are infinitely tall because we have so much mass that to tunnel through it has extremely low probability. So you can see that from the equation from last homework that's in the book that writes the actual probability. They actually explicitly write this as an integral, which isn't as interesting as, when you get the numbers, it's like, okay, great. But imagining this as just imagining your wave function propagating into other, you have a wave function, and it propagates into other surfaces, but it just decays so much in any surface that the probability that you'll be observed on the other side is extremely small. Anyway. So, what was I talking about? Oh, the question was about that. Yeah. So the question was about doing this problem, which is the same one, but it's just shifted in a different coordinate system. And the big thing was that you get even and odd wave functions. You don't all get the same kind. You get even and odd. We know you could get even and odd because in the middle we have sine and cosine. That's the big thing. Because we know we have sine and cosine, these are odd and these are even.
Which
Let me-
one's odd again?
This one is odd
Sign's odd. Okay.
because sine of minus x is equal to sine x. Oh, sorry. Minus sine x. Cosine of minus x is equal to cosine x. This is even. So you can imagine this statement means it's a mirror, right? The same value appears on the left side as the right side. This means that the negative value appears on the right side as the left side. This is odd. But anyway, the whole point is that this wave equation has a solution that is a linear combination of these. So you have to, it's not like only this one works. If only this one works, you could not ever get an even solution because there's no even functions that solve it. But the fact that you get both means you could have even or odd. Or neither. If you just add them together in some weird combination, you could get like a really weird wave. Like if it starts here or whatever, this is not, you could pick a place where it wouldn't be even or odd. Most functions are not even or odd, so it's not a big deal, but anyway. Okay. Do we have any questions? So sort of what we're doing is just like last semester we've been solving second order differential equations, and they give us like integer things in our solutions. Again, I can't say it again, the good heartstring, that we solve it, we get things that look like this, things like this, because something has some sign thing has to be 0, n isn't therefore an integer. And this is a quantization thing, and kind of all we're doing in this whole year so far is doing these problems just for different systems. Except we're not just using like the tension of a string just to do F equals ma as a differential equation like we've been doing for a spring and a string. But we're doing specifically the Schrodinger equation, which is just another thing, and then we're doing some weird things where we square it, but we're not really doing anything that different. So that's why you were saying you understand this better than the other things. I think it's because we're spending sort of an actual good amount of, like an appropriate amount of time on this, as opposed to a week and then you better learn
But
it.
I
Or
feel like I've also seen it previously. So
Yeah, that
maybe the
too.
second
it
time.
relates. I keep pointing to things that that I erased, but the SPDF.
Yeah.
I was going to say SPQR, which is the name of the Roman Empire. Anyway, I don't know why I was thinking of that, but SPDF, yes. Those are things you've already learned about. So this is like just seeing where they come from, not in a super convincing way, but anyway. Yeah. Is that fun? All right. Well.
Do you get what I did?